Okay, so this is our second video focusing on geometric growth and decay. So in terms of financial applications, that was compound interest or reducing balance depreciation. And like we did with linear growth and decay, what we want to be able to do, we've looked at how we model it using a recurrence relation, but now what we want to look at doing is establishing a rule. The difference being the recurrence relation only allows us to move from 1 year to the next year. So if we want to know the value of an investment after 20 years, we have to do the recurrence relation 20 times, okay? What a rule enables us to do is substitute n equals 20 into the rule and get straight to the 20th term in the sequence without needing to create the 19 terms in the sequence before that. Okay, so that's what we want to look at here. As I said, when we did this for linear growth and decay, we need to be a bit cautious about this because in a couple of lessons' time, when we'll start to talk about loan situations where we're combining geometric growth and decay and linear growth and decay. So for example, a compound interest loan where we make repayments, so we earn interest, we multiply by a value to earn interest for the compound interest, and then we subtract a value for the repayment. Where we're combining those two things together, it's not possible to create a rule that enables us to get straight to the 20th term, for example. It's only possible if we're only doing linear growth or we're only doing geometric growth. Okay, look, we'll say it is possible, but it's beyond the scope of this course to do that, and we'll look at other methods for analysing those particular loan situations. But in terms of equation, we just stick with recurrence relation, and we then need other tools. Okay, so as we saw with linear growth and decay, it would be better if we could create a rule that connects the value of the investment with the number of time periods. So we have the value after n years equal to some rule that's got n in it. So we can just substitute n into the rule when we want to know 20 years, for example. So let's have a look at a compound interest problem where $1,000 is invested at a rate of 8% per annum compounded annually. The recurrence relation for this situation would be this. Okay, we're multiplying by 1.08 every year to increase by 8% every year. So what we see happening here is we know that to get the value after 1 year, we take the value after 0 years and we multiply by 1.08. Okay, we know that. And then what we've looked at with the recurrence relation is to get the value after 2 years, we take the value after 1 year and we multiply by 1.08 again. But what we want to think about is, okay, but what about if I want to get straight from here to here? So what we've actually done is we've multiplied by 1.08 and then we've multiplied by 1.08 again. Now when we multiply something by 1.08 twice, so essentially the calculation we've done to get here is 1,000 times 1.08 times 1.08. This is 1.08 squared. So we've times 1,000 by 1.08 twice, which means it's times 1.08 squared. Okay. If we want to look at getting V3, we know we can get V3 from V2 simply by multiplying by 1.08. Okay. But we want to think about how do we get straight from V0 to V3, and the process that takes us there is that we have multiplied by 1.08 once to get to V1, we multiplied by 1.08 twice to get to V2, and to get to V3 we've multiplied 1,000 by 1.08 3 times. So that is 1,000 times 1.08 cubed, which means times 1.08 times 1.08 times 1.08. Alright, and the same logic to follow 4 times. Yes, to get from V3 to V4, we're multiplying by 1.08, okay? But to get from V0 straight to V4, we've multiplied by 1.08 to get to V1, again multiplied by 1.08 to get to V2, again multiplied by 1.08 to get to V3, and finally, for a fourth time, multiplying by 1.08. So to get from V0 to V4, we've taken V0 and we've multiplied it by 1.08 4 times, so to the power of 4. Okay, so let's extend that logic then. V10 would therefore be 1,000 multiplied by 1.08 10 times to get from V0 to V10. So 1,000 times 1.08 to the power of, to the power of 10 is 2158.92. To get to the 25th term in the sequence, so the value after 25 years, it would be the original value, which would have been multiplied by 1.08 25 times. So I can edit my previous calculation here, just change my power from 10 to 25. And so the value of the investment after 25 years would be $6,848.48. So having started with only $1,000 in 25 years, you've got almost 7 times that amount. So compound interest really starts to grow quite quickly once you get to sort of biggish values of n. All right, and then to generalize that, so after n years, we would be taking our initial value, which in this case is 1,000, and multiplying it by 1.08 n times. So generally speaking, if our recurrence relation is this, and again, sorry, like in the linear, this one's missing important part of the recurrence relation, so you must have V naught, okay? So if V naught is whatever Vn plus 1 is found by multiplying by a value, then we can extend that to a rule. It becomes the value after n years is V naught multiplied by that multiplying factor, in this case 1.08 to the power of n, okay? So we're just generalizing that. So obviously if we have compound interest, that capital R value is calculated by doing 1 plus R over 100 because we're growing, it's a percentage increase. If you've got reducing balance depreciation, your capital R value is less than 1 or between 0 and 1. So you calculate your capital R value by doing 1 minus R over 100. Okay, so capital R and capital R are going to be slightly different. Again, I encourage you to really think about being able to logically work out that multiplying factor. So if we're increasing by 20%, we're ending up with 120% of what we started with. That is 1 multiplying by 1.2. If we're decreasing by 20%, we're ending up with 80% of what we started with. That is to multiply by 0.8. Okay. All right, let's work through some examples. Following recurrence relation can be used to model the depreciation of a car with a purchase price of $42,000 and annual reducing balance depreciation of 10.5%. Okay, so again, we're missing the V naught in the recurrence relation, so let's make sure we include that. It's not a recurrence relation without both parts. So V naught is 42,000. Vn plus 1 is Vn multiplied by 0.895, and that 0.895 comes from doing 1 minus R on 100, which in this case is 1 minus 10.5 on 100, which is 0.895. Or you might think about it like I do, depreciating by 10.5% means we're getting 100% minus, we're going to be left with 100% minus 10.5%, which is 89.5%. Percent means divide by 100, so that is 0.895 as a decimal. Okay. All right, so the recurrence relation we've been given matches the information in the stem of the question. Use the recurrence relation to find the value of the car after 1 and 2 years. Okay, so V1, sorry, and then V2. Okay, so 42,000. We multiply that by 0.895, so the value after 1 year is $37,590. The value after 2 years, we again multiply by, just press enter, again multiply by 0.895, and it is $33,643.05. Find the rule for Vn to describe the value of the car after n years. Okay, so the value of the car after n years is the initial value of the car, which in this case is 42,000, and then it's been multiplied by 0.895 n times. So that's our rule, as different from the recurrence relation. It's really important that you understand the difference between those two. If the question asks you for the recurrence relation, it must be what's written up the top here. If the question asks you for the rule, it must be Vn in terms of n, so it must be what's written in part B. Calculate the value of the car after 5 years. Okay, so V5 is going to be $42,000 multiplied by 0.895 to the power of 5. So 42,000 times 0.895 to the power of 5. So that is $24,119.29 to the nearest cent. Let's just be clear, if you continued with your recurrence relation, 42,000, multiplying that by 0.895 once, twice, 3 times, 4, 5 times, you get the same value. Okay, so it's doing the same thing, it's just writing it in a different way. It also means it's going to be easier to work out the value after 100 years. We don't have to hit enter on our cows 100 times, which we would with the recurrence relation. We can just substitute n equals 100 into the formula. Okay, the car would obviously be dead after 100 years anyway, but just the point that we can get further on in the sequence more quickly with the rule. Part D, after how many years will the value of the car have halved? Okay, the original value of the car was $42,000. Okay, half the value is going to be $21,000. So we want to know how long will it take for the value to be $21,000. Find the value of n if the value is $21,000. So 21,000 equals 42,000 multiplied by 0.895 to the power of n. We can get our CAS to solve that. So solve 21,000 equals 42,000 times 0.895 to the power of n, comma n. Solve it for n. Oop, out of the power, comma n. And we find that n is approximately 6.25 years. Okay. Now again, with the rounding here, you need to make sure that you round up, because if we only go for 6 years, it won't quite be halved. It'll still be more than half. So if we have a look at it, we can work it out. 42,000. If we sub 6 into our rule, 0.895 to the power of 6, the value of the car is just a bit more than 21,000 still. So we would need to have a power of 7 for the value to be at least half. So therefore, after 7 years. Okay, again, I'm going to skip over the section which is about using function definition and function notation. If you're a methods student who does further maths, thinking about how your understanding of function notation could be helpful here in defining a function for your rule, and then it's quick and easy to substitute into that. But I'm not going to talk about that as a further maths technique. Alright, example 2, the value of an investment after n years, Vn, can be calculated using the rule. Vn is 4,200 times 1.085 to the power of n. How much money was initially invested? Now, we could work out V0, okay, if we want, but we really should be able to see from the rule what the initial investment is. 1.085 to the power of 0. If you type that in your CAS, or if you know anything about index laws, you would know 1.085, that this is just going to be equal to $4,200. So you should be clear about, in these rules, that value there is your initial value, 4,200. What is the annual compound interest rate? Okay, so that's where this is important. Every year we are multiplying by, so it tells us ends in years. Every year we're multiplying by 1.085, which is 108.5% of the previous year. So it is an 8.5% per annum interest rate. As I said before, if you need to use your rule, you know that R is equal to 1 plus R on 100. So in this case, 1.085 equals 1 plus R on 100. You can get your CAS to solve that equation for you. 1.085 equals 1 plus R on 100. Solving for R, 8.5. Okay. Find the value of the investment after 8 years. So value after 8 years is going to be 4,200 times 1.085 to the power of 8. 4,200 times 1.085 to the power of 8 is going to be $8,066.54. After how many years will the investment be worth more than $25,000? Okay, so again, we want to make the value $25,000 and work out what does n have to be. Okay, so it is $25,000. It's going to be 4,200 times 1.085 to the power of n. We want to solve that for n. So 25,000 equals 4,200 times 1.085 to the power of n. And then comma n, we want to solve that for n. And so n is approximately 21.87 years. Okay. Again, if we round down to 21 years, it won't be worth more than 25,000. So for example, if we were to work that out, 4,200 times 1.085 to the power of 21 would only be 23 and a bit thousand. So it has to go up to, we have to round up to 22,000 to make sure, to 22,000 to make sure that we have more than $25,000. Okay, so therefore after 22 years. Okay, example 3, final example for this video. Jennifer invests $12,500 in an account with an interest rate of 5.1% per annum. Find the value of the investment after 3 years if interest is compounded annually, if interest is compounded quarterly, if interest is compounded monthly. Okay, so again, like we looked at in the previous year, changing the compounding period, you're always going to be given your interest rate as a per annum interest rate, okay? So if our interest is compounded annually, in our formula, n is going to be in years, okay? And we need to work out, and we know that the interest rate is 5.1% per annum, so R is going to be 5.1, which means if you need to work out your capital R value, it's 1 plus 5.1 over 100, which in this case will be 1.051. Okay, so our rule then, Vn, is our initial value, 12,500, multiplied by R, which is 1.051 to the power of n. Okay, so if we want to know the value after 3 years, that is when that's V3. So 12,500 times 1.051 to the power of 3. Okay, 12,500 times 1.051 to the power of 3. Okay, $14,511, and to the nearest cent, that will be 70 cents. Okay, if the interest is compounded quarterly, then n is going to be in quarters when we set up our rule. Okay, and R is going to need to be 5.1 divided by 4. Okay, which is 1.275, which means uppercase R, the multiplying factor, is 1 plus 1.275 over 100, which if we work that out, 1 plus this number divided by 100 is 1.01275. Okay, so our rule for the value after n quarters is again the initial value, 12,500, multiplied by the capital R value for the quarterly interest rate, okay, so 1.01275 to the power of n. Now, if we want the value after 3 years, 3 years is there's 4 quarters in 1 year, so there's 12 quarters in 3 years. So 1,500 multiplied by 1.01275 to the power of 12. Okay, so it's going to be 12,500 multiplied by this number we worked out up here to the power of 12. Okay, so it's $14,552.48. So we expect that that's bigger than that. We're compounding more frequently, therefore we're calculating more interest on interest, and therefore the value after the same time period should be a bit more. All right, let's go again if we're compounding monthly. So this time n is in months when we write our formula. Our interest rate is going to be 5.1 on 12. 5.1 divided by 12. Okay, so that is 0.425. Our capital R value is 1 plus 0.425 on 100. So 1 plus this value I've just calculated divided by 100 is going to be 1.00425. Don't round those values off. It's important that you keep those interest rates exact. Which is why it's helpful, in your CAS to be able to just use your previous answers. Particularly, there'll be some times where it's a repeating decimal that goes on forever. Don't round it off. Use it precisely in your CAS just by copying your number down wherever you need it. Okay. So our rule for n months, the value after n months, is the initial value, 12,500, multiplied by our monthly multiplying factor, which is 1.00425 to the power of n. Now, if we want the value after 3 years when we're in months, that's the value after 36 months. So 12,500 multiplied by 1.00425 to the power of 36. Okay, so 12,500 plus this number we just worked out up here to the power of 36. Sorry, I've typed something in wrong there, haven't I? Sorry, I realised I didn't, I typed, instead of multiplying, I've typed addition in the CAS. So, you know, that little bit of does your answer make sense? I'm expecting the answer to be bigger than this. So the minute it was only 12,000 and something, I know that I've done something wrong. So stop, go back, have a look, see where you've gone wrong. So in my CAS, you'll see here, I typed plus in the rule where it shouldn't be plus, it should be multiplied by. Okay, there we go. So $14,561.84 to the nearest cent. So again, you know, it's a bit more. So it was only 14,511 with annual compounding, 14,552 with quarterly compounding, and then 14,561 with monthly compounding. And that's only after a 3-year period. You extend that out to a 30-year period on a home loan, and you're talking about a big difference in the money. Okay, so exercise 8F was the work for this section.